Yeah, so I'm gonna, so the main goal is to explain some conjectures, which are checked in a couple of cases, and there's some evidence for them. So I'll motivate them with some theorems, and then formulate some conjectures. So my talk is gonna consider two cases simultaneously, and I'm gonna try to keep to this pattern where the quantum case goes on the left side of the screen, and the reductive group case goes on the right side of the screen. And broadly speaking, the stuff in the quantum case is theorems, mostly due to Lusztig, Ostrik, and Bezrukavnikov. And the stuff in the reductive case, oh no, the word case is up there twice. There are some theorems, but I think the stuff I really want to focus on is in the reductive group case is not a theorem. So here's the setup. So this bold-faced letter K, it's going to be the ground field in both cases. So in the quantum case, it's the complex numbers. In the reductive group case, it's algebraically closed and a positive characteristic. And so I'm going to have some slightly unusual notation. So this this letter G, it might be either a quantum group or a reductive group. So you have to get used to the idea that the G might be a quantum group. And when it's a quantum group over the complex numbers at an Lth root of unity. And of course, on the reductive group side, it's a reductive group. And in both cases, I want to assume that the either L or P respectively is larger than the Coxeter number. And then there's some notation that's common to both cases. So of course, later on in the talk, I'll have the Weyl group and stuff like that showing up. But for right now, so I have the weight lattice that's called X, dominant weights X plus. And for any dominant weight lambda, there's an indecomposable tilting module whose highest weight is lambda. And that's called T of lambda. So one important fundamental fact about tilting modules is that they're closed under tensor product. So the additive category of all tilting modules is a tensor category. And if, of course, there are some people in the audience who are experts on tilting modules. If you're not used to thinking about tilting modules, I'm going to have some pretty concrete examples on the next slide that's going to sort of illustrate the kinds of things I want to consider. And so one basic notion that's going to be omnipresent in the talk is the notion of a tensor ideal. So this is just what you think it means. So it's a full additive subcategory. By the way, can you see my mouse cursor on the sharing screen?
Yes.
Okay. So Anyway, I guess I can use it sometime to highlight things. So tensor ideal is a full additive subcategory. So it has to have the ideal property, which means if you multiply means tensor by any object, you stay in the ideal. And then it should be closed under direct sum because it's an additive category. So when you say tensor ideal, so I think maybe some people use the word thick tensor ideal to clarify this. There's a difference from the notion of ideal in just a ring, which is that it has this extra property of being required to be closed under direct summands. So if you have anything in the ideal and you decompose it all into indecomposable things, all those indecomposables have to be in the ideal. Okay, and then of course, principal tensor ideal is something generated by one object, and I want that object normally to be indecomposable. Okay, so a motivating problem for the entire talk is to classify the principal tensor ideals. And just to warm up, I'll tell you the solution in SL2. So SL2, so I'll tell you the solution in both the quantum and the reductive cases. So this is a nice concrete example. And so of course the dominant weights for SL2, you can identify with the non-negative integers. So here are some specific examples of tilting modules. The tilting module of highest weight 0 is the trivial representation. The tilting module of highest weight 1 is the defining representation of SL2. And then, so I mentioned that tilting modules are closed under tensor product. So of course, if you take tensor powers of T1, you get tilting things. And in fact, you get everything this way. So all indecomposable tilting modules are of the form T of M. And this occurs as a summand of the mth tensor power of T1. So of course, the way this decomposes depends on which situation you're in. So if you're in the quantum case, it depends on L. In the reductive case, it depends on P. So I want to say a little bit about that. So that means that, you know, like the dimension of this tilting module depends on the specific situation you're in. And I want to discuss some examples, and I want to start with example 0, which is SL2 over the complex numbers. And this is actually not one of the cases on the previous slide. It's not a quantum group, and it's not a reductive group in positive characteristic. It's easier than both of those because, of course, for semi-simple complex algebraic group, every representation is completely reducible. And so you don't usually talk about tilting because it's a trivial concept. Every module for SL2C is tilting, and T of M just means the irreducible of highest weight M. But right, so it's a useless concept, but you can still talk about it. So I want to tell you the classification of tensor ideals for SL2C, and the answer is there's only one, and here's the proof. So the only principal tensor ideal is the entire category, which you could call the unit ideal. And the proof is that if you take any indecomposable like T of M and you tensor it with its dual, which is of course itself. I mean, I just put the dual sign there to, I don't know, remind you that I'm taking the dual. This tensor product contains the trivial module as a direct sum end, and then as soon as your ideal contains the trivial module, it's got to contain the entire category. So in SL2C, there's only one principal tensor ideal. The next case is quantum SL2 at an Lth root of unity. In this case, it turns out that there are exactly two principal ideals, and here's what they are. So if you take a highest weight, which is between 0 and L minus 2, then the tensor ideal that you generate is the entire category. So it's the unit ideal. And if you take any other weight, any weight bigger than L minus 1, then all of those tilting modules generate the same tensor ideal. And it's, I mean, it doesn't, well, anyway, it's the unique principal tensor ideal other than the entire category. So people who are interested in tensor categories maybe have seen, would be used to this from the perspective that you want to take the quotient of the whole category by this proper subcategory, and then you get a semi-simple abelian category, semi-simple tensor category with exactly L minus 1 simple objects. So that's an example that's of interest. And then in the reductive group case, so this is different from both of the previous two cases. In this case, there are infinitely many principal tensor ideals, and here's the classification of them. So to tell you the classification, I need a tiny bit of notation. So if I take a non-negative integer, I want to let nu of M be the, well, yeah, I guess this is the shortest way to say it. So I want to write out the p-adic expansion of M plus 1 and take note of the largest power of p that occurs in that p-adic expansion. And whatever that is, I want to call that nu of M. And then one can show, so I know there's an old paper of Anderson that contains this statement. I mean, I don't know if it, I mean, it contains some more general statement that covers SL2 as a special case. I don't know if it was known before that, but anyway, it turns out that the principal tensor ideals for SL2K are classified by this invariant. So two tilting modules generate the same tensor ideal if and only if this largest power of p in the p-adic expansion is the same. Okay, and then there's a kind of a numerology phenomenon here, which you should expect if you're familiar with kind of the parallels between quantum groups at roots of unity and reductive groups, which is that the description I gave up here of what happens in quantum SL2, it looks like just paying attention to whether the L-adic expansion of M contains positive powers of L or not. Or sorry, of M plus 1. Yeah, so you take M plus 1, take its L-adic expansion, and you either get, it either has powers of L or not. So, okay, so that's a complete solution for SL2. So now let me tell you, so the title of my talk had 3 topics in it. So these are the topics. I had tensor ideals, P Kazhdan Lusztig cells, and I had nilpotent orbits. So far, I've only told you about kind of examples of tensor ideals. So in the next couple of slides, I want to tell you about peak Kazhdan Lusztig cells, and I'm going to tell you about this arrow right here. So before I do that, I want to introduce some language. This isn't really essential, but for me, it's a convenient way to talk about a couple different concepts in a unified way. So it's the language of based rings. So I want to start with a commutative ring. I wrote usually here, but I actually mean always. It's either the integers or Laurent's polynomials in one variable. And then I want to take a commutative, sorry, not R is not necessarily commutative. I want to take an A algebra, which is free as an A module, and that comes with a specified basis called curly B. And so for such an algebra, I want to make a definition. So a based ideal is just an ideal that's also a free A submodule and is spanned by some subset of the specified basis. So that's a very restrictive condition. If you take sort of a random ideal, of course, it's not going to be based. And then a principal-based ideal means this: if I take any element of the ring, I can take the smallest based ideal that contains it. So just to think about this intuitively, of course, if I left out the word based, I would just mean take X and multiply on the left and right by elements of the ring. And now to take the principal based ideal, I want to multiply on the left and right by ring elements. And then I also want to be able to take, I want to take any element that I know is in the ideal. If I expand it in this basis, then the terms of that expansion should also belong to the ideal. So that's what this is. So of course, the principal based ideal is often much bigger than the principal ideal generated by X. And here are some examples. So if I take the tensor category of tilting modules, and I take its split Grothendieck group, well, this is a ring because, of course, this is a tensor category. And it's a free abelian group with a basis given by the classes of the indecomposables. And so something that you can see basically immediately from the definition is that a principal based ideal with respect to the specified basis is exactly the same concept as a principal tensor ideal. So this categorical notion is the same as this kind of easy ring theory notion. Here are a couple other examples. So for example 2, I want to take an extended affine Heck algebra. Actually, for right now, the fact that I have the word extended and affine here, it doesn't really make a difference. Oops. If you want to think of the finite Heck algebra or the plain affine Heck algebra, that's also perfectly fine for right now. So this has several different bases that I want to consider. The easiest basis you might think of is the so-called standard basis. That's the one where you write down generators and relations for the Heck algebra. In the standard basis, every basis element is invertible. And so it's automatic that any based ideal has to be the entire ring. So the unit ideal is the unique based ideal. So that's not a super interesting example. Then the next thing you could look at is the Kazhdan Lusztig basis. And in this example, I mean, I didn't specify over here what kind of ideal I meant, but of course you can consider left, right, or two-sided based ideals. And these are exactly the same concept as left, right, and two-sided Kazhdan Lusztig cells. And this is the reason I wanted to introduce this language. When I was a student a long time ago, when I first read the definition of Kazhdan Lusztig cell, well, of course, the definition is elementary, but it took me a long time to kind of get it. But I feel like if you just say, well, it's based ideals with respect to some specified basis, then that's anyway, that's much more concise than writing down a pre-order and then telling people to take some equivalence relation. But it's the same concept, so that's easy to see. And then, in the past 10 years or so, now you can consider another basis for the Heck algebra, which is the p-canonical basis, and then you repeat this. So the p-canonical basis is some basis for the Heck algebra, and then left, right, or two-sided ideals with respect to this basis. That's the definition of left, right, or two-sided p-cells. Okay, so those are some situations where you can apply this concept. And here's example 3. So now it makes a difference that I took the extended affine Hecke algebra. So I want to define a module for it where I take, so this HF in the subscript here, that's the finite Hecke algebra. I'm going to take the sign representation of the finite Hecke algebra and then tensor up to get a right module for the extended affine Hecke algebra. And this is called the anti-spherical module. And I think this made an appearance in either Laura or Roman's talk earlier in the week. This is not a ring, it's a module, but it comes, I mean, it inherits bases from the extended affine Hecke algebra. It inherits both a Kazhdan Lusztig basis and a p-canonical basis. I mean, it inherits a standard basis too, but that's somehow less interesting. And then you can sort of copy this idea of a principle-based ideal. You can look at principle-based submodules in the anti-spherical module. And those submodules are called anti-spherical Kazhdan Lusztig cells or anti-spherical P cells. Okay, so I want to use this concept, this concept of anti-spherical cells. So these are exactly principle-based submodules in the anti-spherical module to tell you a theorem about the motivating problem. So here's a statement of the theorem. The quantum case is due to Ostrik, and the reductive case, well, it's due to I mean, Weyl, Hardesty, and Riche, and I wrote it down. I'm going to sketch the proof, and it's actually, the proof is identical to Ostrik's proof. It's what we did was just sort of observe that you can copy Ostrik's proof in the reductive case. And the proof sketch goes like this. So principal tensor ideals that are the same as principal based ideals in this ring. Anti-spherical cells are principal submodules in this ring. Well, actually, anti-spherical cells are in the, I mean, they're in the anti-spherical module, which lives over Laurent series and not over the integers. So you have to specialize this by setting v equal to 1. But once you specialize it, you can define an explicit map from this abelian group to this abelian group. It's slightly tricky because this this map is not a map of modules over the Hecke algebra. It's something else. It's well, anyway, it's just some map of abelian groups. But once you write down the map, of course, the main thing you need to show is that alpha matches up based ideals in this ring with base submodules over here. And then the key to doing this is the fact that the anti-spherical module controls characters of certain tilting modules. So in the quantum case, there's a character formula due to Zergel from about 20 years ago. In the reductive group case, there's a character formula which was proved by myself and Makisumi and Riche and Williamson a couple of years ago. There's now a super slick proof of it, a new proof of the same formula due to Riche and Williamson, which is on the archive from a couple months ago. And anyway, these theorems say that these bases, either the Kazhdan and Lusztig basis or the p-canonical basis for the anti-spherical module, describes tilting modules for certain, sorry, characters of tilting modules for certain tilting modules, and that's kind of enough to prove this. Okay, so so now I've written down 2 bijections, so that's kind of an answer, right? Like if my goal is to classify principal tensor ideals, well, now I've told you here's an answer in terms of something that feels kind of computational. But if you don't know what the anti-spherical cells are, this isn't a useful theorem yet. So how many anti-spherical cells are there? Okay, so let me tell you the answer to that in the quantum case. So I need to introduce some new notation. I want to use boldface G. I hope the boldface G looks different enough from the other G's. So boldface G in both cases, it's a reductive group. In the quantum case, I want it to be the reductive group over the complex numbers with the same root datum as your quantum group. And in the reductive case, it also has the same root datum, but it's not kind of equal. I want it to be the Frobenius twist. Of course, in the reductive case, G is isomorphic to its Frobenius twist, but it's morally a different group. And actually, in both cases, boldface G is kind of the target of Frobenius. And in the quantum case, Lusztig's quantum Frobenius takes you from the quantum group to the enveloping algebra, this reductive group. So boldface G, what you should think of as target of Frobenius. And boldface G has a nilpotent cone, and it acts on that nilpotent cone with finitely many orbits. And here's a theorem of Lusztig that goes way back to the 80s. The theorem says that there's a canonical bijection between anti-spherical Kazhdan Lusztig cells and nilpotent orbits. And so in particular, a consequence of this, which is not at all obvious from the definition, is that they're finitely many anti-spherical cells. And we can go back to our example of quantum SL2. In fact, there are exactly two anti-spherical cells for SL2. So I've told you sort of everything that fits in every part of this diagram. From my very first slide, the tensor ideals, well, here's what they are. There's the unit ideal, and then there's the ideal generated by the Steinberg representation, which has highest weight L-1. For nilpotent orbits, this is linear algebra. So you learned in undergrad that the conjugacy classes of 2 by 2 nilpotent matrices, well, there's two of them. There's the zero matrix, and everything else is conjugate to this nilpotent matrix. And then, there are also exactly two anti-spherical cells. On the other hand, in the reductive case, well, this theorem, if you just copy the statement, there's no way it's going to be true, because there are still only finitely many nilpotent orbits, but there are infinitely many tensor ideals, as we already saw in SL2, and then the previous slide implies that there are also infinitely many anti-spherical P cells. Oh yeah, and also earlier in the talk, I had a third arrow along here. So what I need to do in the rest of the talk is I need to explain how to fill in this bottom arrow in the quantum case, and in the reductive case, I need to tell you about everything. So I guess now is a good time to take a break.
And Pramod, this is Monica, hi.
Hi.
If you can multitask while you're sending the email, ask you a question, but if you want to focus on the email, I can wait.
Yeah, you can ask the question.
Okay. Well, so if you go and look in the chats, so I had asked about, why to expect anti-spherical instead of spherical, and Roman gave some good answers to that, but I thought I would give you a chance to read the comments and or give your perspective on that.
Okay, so let me figure out, there's probably some philosophical answer about how, right, so the anti-spherical module has to do with, so you tensor up from the sign representation, which means you make the generators of the finite Weyl group act by -1. And there should be some philosophical answer where you sort of see this as a shadow of how translation functors act on the principal block of the group. It's probably more than philosophical. I mean, probably there's a way to make that precise, but yeah, I don't know if I can say something very precise on the spot.
And thanks, Roman, too, for the chat.
Yeah, no, I'm just expanding on your comment that the translation functors, they have to do, if you see what they do on the K group, this is action of some element which is a cyanide important for this small subgroup. If you crossing them with the cyanide important for this thick algebra of SL2. Oh, yeah. So that's indication that they are nicely compatible with the anti-spherical picture.
Well, you know that in the characteristic P case for algebraic groups, in addition to the tilting modules for the entire algebraic group, there are so many Frobenius kernels.
Sure.
And there are also their tilting modules, and also their injective modules, and they all form quite a nice basis. So how are all those kind of correspond, and how do they correspond in terms of cells?
Yeah, so I don't know the answer to that. So yeah, so I know very little about higher Frobenius kernels. So somehow Yeah, this is going to show up later in the talk, actually. I mean, somehow the first Frobenius kernel, I mean, there are a lot of analogies with the quantum group situation. And so that gives you some place to start thinking about them. I mean, I think, yeah, I mean, there's some hint at the end of Roman's talk about ways to start understanding higher Frobenius kernels. So I think, yeah, I think I don't have anything useful to say about higher Frobenius kernels.
Okay. I thought you might be definitely look at for the first Frobenius kernels, because
yeah.
And more interesting would be the piece power of the roots of the quantum group for the different powers of P of roots of units.
Well, so somehow in the quantum group case, like L doesn't have to be prime. It doesn't.
L can be anything, but in particular, if you take L to be for each power of P, to be L, and you have infinite many families of quantum groups at the root of the unit, and they all were. I mean, each one of them gives a cell, because you were using the antispherical module, but how corresponding to the weight lattices depends on what the L is, how the L is acting on the weight lattice. Basically, you translate by multiples of L. I'll be looking forward to the rest of your talk to see.
Okay, so is it time to start again?
Yeah, you can restart. I'll have your slides in a moment.
Okay. 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 Yeah. So right. So so we're just talking about the first Frobenius kernel. So this. So here are some classical results which Roman mentioned in his talk. So I want to use lowercase g to mean the small quantum group in the quantum case, and I want it to mean the first Frobenius kernel in the reductive group case. And so n is still the nilpotent cone in boldface G. So this theorem of Anderson-Janssen and Friedlander partial, this is from the 80s. And the statement is that the X algebra of the trivial module over the first Frobenius kernel is naturally isomorphic to the coordinate ring of the nilpotent cone. And here I want to just remind you that one of the assumptions is that P is bigger than the Coxeter number. So it's so this is not true when P is smaller than that. And then I think in the early 90s, it was a result of Ginsburg and Kumar that the analogous thing is true in the quantum setting, except now it's going to be the complex nilpotent cone. So this X algebra is the complex nilpotent cone. And so so now using these results, here's something I can do in both cases. So if I take any representation of G, I define its small g cohomology to just mean X from the trivial module to M. And of course, I mean, this definition doesn't require you to start with a big G module. You could start with a small G module, and this still makes perfect sense. The reason that, I mean, you get some extra structure though if you start with a big G module, and the extra structure you get is that, well, in any case, I mean, this cohomology, it's a module over this ring or this ring. So you always get a module over this coordinate ring of the nilpotent cone. But if you start with a G module, then this cohomology comes with an action of big G. So of course, a Kn module of the compatible big G action is the same thing as a big G equivariant coherent sheaf on N. And, oh, sorry, I didn't, yeah, I guess that was all I was going to say on this slide. So, yeah, so for any small G, any big G module M, you take its small G cohomology and you get a big G, boldface G equivariant coherent sheaf. Yeah, sorry, yeah, everything is called G. And you could try to figure out if you can understand something about what this coherent sheaf is. So I'm going to tell you some sort of startup, I mean, some warm-up facts to get us going. One is that when you take this cohomology for a tilting module, it's very often zero. In fact, it's zero unless lambda is in the affine Weyl group orbit of 0, under the scaled dot action. So this is this L dilated action that Zhongzhu was just mentioning in the question period. I guess I should have written either L or P down here. So in the quantum case, that should be an L, and in the reductive case, it's a P. But it's not for sort of arbitrary things in the affine Weyl group. I want to take a minimal double coset representative for the extended affine Weyl group modded out on both sides by the finite Weyl group. So yeah, so this thing is very often 0. But on the other hand, it turns out that every principal tensor ideal has a generator where this cohomology is non-zero. So the point is that I'm working towards telling you that this G cohomology is going to be a tool for studying tensor ideals, and you're not going to miss any tensor ideals by taking G cohomology, even though you often get 0. And then there's going to be 2 more statements. So now assume that you have non-zero cohomology. Then it turns out that the support of this coherent sheaf is irreducible. So that means it's the closure of a single nilpotent orbit. And what's also true is that if you have 2 modules that generate the same tensor ideal and that both have non-zero cohomology, then they have the same support. So you get the same nilpotent orbit out of them. And so, yeah, so all these things, all these 4 parts of this proposition together mean you have a map from principal tensor ideals in the additive category of tilting modules to nilpotent orbits. Okay, so here's a theorem. So some form of this was conjectured by Humphreys and proved by Bezrukavnikov. So this is a theorem in the quantum case. So I already told you about this bijection, which is due to Ostrik. This bijection is due to Lusztig. So of course, if you compose these, you get a bijection. And so Bezrukavnikov proved that this triangle commutes. And so in particular, this map that you get directly from the definition of cohomology is itself also a bijection because the triangle commutes. Okay, so that's pretty nice. So the next slide. So I'm just rewritten Roman's theorem here. So in the quantum case, you have 3 nice bijections. Let me tell you what happens in the. Oh yeah. So actually, before I do that, yeah. So this statement, I'm going to call it Humphreys conjectural. The Humphreys originally didn't state it in terms of tensor ideals. He stated it directly. I mean, Humphreys wanted to give a formula for what the support of cohomology is, and actually, even that's a bit of a lie. Humphreys' formulation was, yeah, it was something slightly different, but it was close enough. So it's less of a lie to say that Humphreys conjectured this. So he conjectured a formula for the support of the cohomology of any tilting module, and he gave a formula which is in terms of antispherical cells. There's no mention of tensor ideals, but once you have Ostrik's bijection, then Humphreys' conjecture becomes equivalent to saying that this triangle commutes, and that's what Roman proved. All right, so in the reductive case, here's a theorem which was proved by Will Hardesty for SLN, and in general by the 3 of us. But I need to warn you that for SLN, it's true as soon as P is bigger than the Coxeter number, which is N. And for general G, we need to require P to be bigger than some unknown bound. So when P is sufficiently large, and of course we expect it to be the Coxeter number, but that's not proved. Okay, so this arrow was in the first part of the talk. This is a bijection that we already had. This is easy. What we proved is that the map along here is given by Humphreys' formula. So the thing is that Humphreys' conjecture, well, it's the same map as in the quantum case. It's a formula for the support of the cohomology of a tilting module and involves Kazhdan Lusztig cells, not P cells. So what we proved is that this map is the map that was conjectured by, I mean, it's given by the formula that Humphreys conjectured. But there's no commutative triangle here yet because there's no arrow here at all. And also this map is not a bijection. I mean, it's obviously not because this set is infinite and this set is finite. So so it's kind of unsatisfactory. So in the left-hand part of the screen, Roman's theorem gives us 3 nice bijections. In the right-hand part of the screen, we've got 1 bijection, 1 surjective map, which is unrelated to it at the moment, and then nothing here. So what I want to do for the rest of the talk is explain conjecturally how to spruce this up so that it also has 3 nice bijections. Okay, yeah, so does Roman have a question? Let me, let's see. Yeah, so I got a little.
Yeah, sorry, just a very quick naive question. So it's not true that P cells partition the usual cells.
So it's a consequence of the Humphreys conjecture that P cells partition the usual cells. So that's true for the anti-spherical cells, not in the full affine Weyl group. So for anti-spherical cells, when the Humphreys conjecture is true, the anti-spherical cells partition, the P cells partition the Kazhdan Lusztig cells.
So under this condition, you have an arrow, right? From
yeah, that's true. Yeah. I mean, yeah, you can define it. Yeah, that's true. Yeah, that's true. Yeah.
Okay, thanks. But so Humphreys conjecture, which maybe you'll say later, right, about the status.
Yeah. I mean, it's just it's true when P is big enough for any G, and it's true for SLN when P is bigger than N.
Okay, thanks.
Okay. Let's see. So right. So the goal for the rest of the talk is to explain how to spruce up this picture, and to do that, I want to get into some more details about what's going on in the quantum case. So this is the diagram of 3 nice bijections that we have in the quantum case. So let me set up a bit of notation. So if I have a nilpotent orbit and I pick a point in it, then of course coherent sheaves, equivariant coherent sheaves on the nilpotent orbit is the same as representations of the stabilizer of a point. And the stabilizer of a point is usually not a reductive group. It usually has some unipotent radical, but you can mod out by that, and then you get something called GX red. This is a reductive group. One caveat is that this may be disconnected, but that I'm not really going to worry about that. But anyway, this is a quotient, and so of course you can think of this as a subcategory of this consisting of representations that factor through this quotient. And so then you can like transfer some language from representations to coherent sheaves. So yeah, so also every coherent sheaf is of course locally free, so it's a vector bundle. So a vector bundle in CoGO is said to be irreducible if it corresponds to an irreducible representation of one of these groups. And that also just literally means it has no proper subcoherent sheaf. Here's another theorem of Roman that's sort of tied up with the stuff I already told you about. So in the case where you have a tilting module with non-zero cohomology, so I already told you that its support is the closure of one nilpotent orbit. So if you restrict this to the open orbit in its support, then a theorem of Roman is that the coherent sheaf you get is always an irreducible vector bundle. And not just that, the assignment where you take the label of this tilting module. So recall that this tilting module having non-zero cohomology means that your label comes from some element of this double coset in the extended affine Weyl group. So you get from these double cosets to pairs consisting of a nilpotent orbit and an irreducible vector bundle. And in fact, this assignment defines a bijection. And this bijection, the existence of a bijection more or less along these lines had been conjectured a long time ago independently by Lusztig and Vogel. So sometimes now it's called the Lusztig-Vogel bijection. This theorem, I mean, if you want to get started on this in the reductive group case, the first statement is false already for SL2. So you can compute an example in SL2 where you don't get an irreducible vector bundle. But there's a tantalizing hint of what might be happening instead. So in the examples we can compute, which is not very many, but in the examples we can compute, it looks like when you restrict this cohomology of a tilting module to the open orbit of its support in the reductive group case, instead of getting something irreducible, you get something indecomposable and tilting. So just to clarify what that means, let me go back over here. a coherent sheaf on O is called tilting if it corresponds to a tilting representation of this reductive group. So sorry, because this group is reductive, the word tilting makes sense. So you can talk about tilting vector bundles. All right. Here's Roman's theorem again from the previous slide, so just copied it over. So now we're going to state a conjecture. So this is I guess again this is part of this joint work with Will and Simon. So it starts off the same way. So assume you have a tilting module with non-zero cohomology and let O be the open orbit and support. So in parallel to Roman's theorem, when you restrict the cohomology to the open orbit and the support, you should get an indecomposable tilting vector bundle. Moreover, when you do the same assignment that Roman does, so you still get this set of double cosets in the affine Weyl group as the source of the assignment. And on the right-hand side, you get nilpotent orbits and tilting vector bundles. But now for any reductive group, of course, irreducible and indecomposable tilting, these are canonically in bijection. So even though you have different things here you have irreducible and here you have indecomposable tilting, combinatorially, it's kind of the same set. So part of the conjecture is that this assignment should still be bijection, and it should still be this, in fact, the same bijection, the same one you get in the quantum case. It should still be the Lusztig-Vogel bijection. So we have one short paper explaining that here, like everything on the right-hand side is taking place on nilpotent orbits and positive characteristic, and the left-hand side is taking place on nilpotent orbits and over the complex numbers. So we have a paper explaining that there's a canonical isomorphism of root data of, well, I mean, partly this is due to McNinch and maybe Testerman, but building on that, we explained that there's this idea of matching the Lusztig-Vogel bijection is well defined. You can phrase the Lusztig-Vogel bijection in a way that's independent of characteristic. So that's part of the conjecture. But there's more to this. So the motivating problem from the first slide was to study tilting ideals tensor ideals. And so if you have two tilting modules that have the same support, they may or may not be in the same tensor ideal. And so I want to tell you when that's the case. So if I take two tilting modules that generate the same tensor ideal, then I want that to be the case if and only if they have the same support. And this extra condition is the following. I can take cohomology, restrict to a nilpotent orbit, then I get a tilting vector bundle on a nilpotent orbit. And now I'm in the category of tilting representations of some smaller reductive group. And I can ask whether these tilting vector bundles generate the same principal tensor ideal in this category. And so I want this to be an if and only if. So to summarize this, so here's the main conjecture. So this would be, like, if all of this is true, then this would be kind of as good as Roman's theorem in the quantum case. There should be a commutative diagram of 3 bijections. This one is the only one that's a theorem. This one, there's evidence for, so this one being a bijection, it's true in SL2, SL3, and SO5, and more generally, part of it, I mean, the parts related to maybe the principal orbit, the subregular orbit, and the zero orbit are true in any group. So that's some evidence for this. This arrow is also dotted, and I didn't tell you anything about it yet, and I wasn't sure if I was going to have time for it, but I guess I still have about 7 minutes. Is that right?
Yes, that's right.
Okay. So I'll tell you a bit about this. So this should be, this should have something with tensor categories attached to antispherical cells. So I want to let boldface B be a Kazhdan Lusztig cell, and then Lusztig defines some category which I'll call AC. I think this doesn't exactly match the notation in the literature, but anyway, I'm going to call it AC for now. and it's some subquotient of the category of semi-simple perverse sheaves, Iwahori equivalent perverse sheaves on the affine flag variety. And a non-trivial fact about it is that it has a monoidal structure. It's induced by convolution on the affine flag variety, but so we learned, we heard something about convolution on the affine flag variety in Laura's talk and in Roman's talk. This convolution is not T-exact. Nevertheless, there is some version of it which induces a monoidal structure on this category, which is an abelian category. And this category categorifies part of something called the asymptotic Hecke algebra. And the way you get the asymptotic Hecke algebra is you take the ordinary Hecke algebra, the ordinary, affine or extended affine Hecke algebra, and you modify its structure constants in the Kazhdan-Lusztig basis. And so a theorem, so these three people had a series of papers with a title something like on tensor categories attached to cells in affine Weyl groups. Anyway, there's lots of results in there, but one of the results that you can extract from there is that this monoidal category is equivalent to the tensor category of representations of this reductive quotient of the stabilizer of an element in the nilpotent orbit. So in the reductive case, I want to state a conjecture. Well, it's weaker than a conjecture because this somehow there are no examples where I know how to compute this. Maybe it's just a hope. So I want to still start with an anti-spherical Kazhdan-Lusztig cell. So Roman's question from earlier is relevant. I'm not starting with a P cell. I'm starting with an anti-spherical cell. Sorry, a KL cell. And the hope is that it's still possible to define a category now, not in terms of semi-simple perverse sheaves, but in terms of parity sheaves, such that, well, it should still have truncated convolution. It should still categorify the asymptotic Hecke algebra. So the weird thing is that parity sheaves categorify the P canonical basis, but I want this thing to categorify something defined in terms of the Kazhdan-Lusztig basis. So there's a lot involved in making this precise. There's some stuff tied up with whether parity sheaves are perverse. So parity sheaves are, there are lots of known examples where parity sheaves fail to be perverse, but maybe on some subquotient category, they behave as though they're perverse. That needs to be the case for this to work out. And if it does work out, then this monoidal tensor category, so it should not be abelian, it should be an additive monoidal category, which is equivalent to the category of tilting modules of this reductive group. And then if all of that works out, then that would fit into, that would fit into the big picture on this slide. So this is a hope, maybe it's not yet worthy of being called a conjecture. And maybe for the very last slide, I'll tell you some combinatorics for GLN. So in the quantum case, if you want to, so the question from the very beginning of the talk was to classify tensor ideals in the category of tilting modules. So in the quantum case, they match up with nilpotent orbits. So I want to talk just about GLN. So of course, nilpotent orbits for GLN are classified by partitions of n. And I want to just give you a little bit of notation for that. So if you have a partition of n, so let me write it out like this. So here, the p's are the parts, and the superscripts are the multiplicities. So I want to let multiply just be the tuple of multiplicities. So general fact is that if you take a nilpotent orbit in GLN, the reductive part of its centralizer is, again, a product of smaller copies of GL. And the sizes of the general linear groups you get are exactly these exponents in the partition. It's the multiplicities. So now let's look at the reductive case. So our conjecture says that tensor ideals in the category of tilting modules should be classified by pairs consisting of a nilpotent orbit and a tensor ideal in this category of tilting vector bundles. But that's the same as tilting representations for a product of smaller GLs. So now you can iterate. You can take this smaller GL, if you want to classify tensor ideals, if you want to just classify these, then you want to look at a nilpotent orbit for this product of GLs, and then look at tensor ideals and tilting vector bundles on its nilpotent cone. And then you can keep going. So when you iterate this process, here's what you get. so the final combinatorial statement is that tensor ideals in tilting modules for GLN in the reductive case should be classified combinatorially by sequences of multi-partitions. And so multi-partition is just a tuple of partitions. So the very first one is just a partition of n. After that, each multi-partition is a multi-partition of the multiplicities of the exponents in the preceding one. And then when k is very large, you should eventually just get the trivial multi-partition. Okay, so that's the end of my talk.
Okay, great. Let me make sure that people can unmute themselves. So people should be able to ask questions on their own now.
May I ask, so the centralizer of an nilpotent is not necessarily connected in groups other than GL. So how do you adapt the theory of tilting modules to that setting? So is the definition of tilting just says that it should be tilting as a module over the connected component?
No, so that's not the definition. So in the so when it's disconnected, so because p is bigger than the Coxeter number, it's guaranteed to not divide the order of the component group.
Okay.
And so when you have a disconnected reductive group where the order of the component group is prime to the characteristic, there's a highest weight structure on the category of representations of the disconnected group. So you can define sort of Weyl modules and dual Weyl modules roughly as you said. Like, I mean, really, it's really
a Weyl module tensored with some representation of.
Yeah, it's something like that. I mean, you should define it in sort of general highest category language, like it's some object characterized by some properties, some X vanishing properties or something like that. So those exist. And then a Weyl module restricted to the identity component is a sum of Weyl modules. But a tilting module, it's not obvious that its restriction to the identity component is a sum of tilting modules.
No, from if
maybe, maybe it is obvious. Yeah. Anyway, anyway, so what you said is not the definition. It's just that there is a highest weight structure. So there
should be some. So you said that you can just say it's a highest weight category and then just use a general theory. But
yeah,
you need partial order, and so partial order is by well, usually it's just usual order on the highest weights, and here there is.
So the component group acts on highest weights, and then the set of orbits for this action inherits an order. Mm-hmm. So that's the so basically irreducibles are classified by orbits of the component group on highest weights, comma some module for some stabilizer. But the partial order doesn't depend on that stabilizer thing. It's just the order on orbits of the component group on highest weights.
Right. And then just last question, so about the GLN case and combinatorics. So is there an algorithm how to produce a sequence from multi-partitions from?
Yeah. I mean, there is. So you have to. I mean, so like if you mean if you take a random dominant weight and you want to know what multi-partition to attach to it? Is that the question?
Yes.
Yeah. So the computation you have to do many times is figure out what alcove, like you have to figure out what alcove, you have to find the affine Weyl group element labeling its alcove. Then you have to find the corresponding thing in this, the minimal thing in the same double coset. And then, anyway, there's a couple of steps, but it's, yeah, it's maybe not very concise to say over Zoom, but there's an algorithm involving, like it comes down to being able to do some affine Weyl group computations. Like you have to know how to compute whether two things are in the same coset, and you have to compute the alcove that some dominant weight is in. That's the kind of thing you have to compute. But yes, in principle, you can compute it.
Thank you.
I have a couple of questions, Pramod.
Yep.
When you were showing how, I'm just trying to get a handle on what's actually happening. The group homology functor, is it like, should I think of it as like a reduction of order thing? So, quantum groups at roots of unity are like a first order divisibility idea, and the tilting modules for that are sent to something like that are actually semi-simple, actually irreducible stuff. So it's kind of like a zeroth order thing. Whereas the infinite order characteristic P thing is sent to another infinite order characteristic P thing. If, geometry hasn't figured this out yet, but if there were something that were nth order, would it be sent to n-1th order? Or am I just...
I guess so.
Because you're taking a Frobenius kernel, which is why I'm asking. Like,
you mean, is there some, I mean, like, isn't there some paper of Lusztig
by
and someone, there is some work of someone else on
his name right now.
I forgot what it is, but like there should be some sequence of algebras or
from
something
Argentina. I'm just trying to
between a quantum group at a root of unity and the reductive group, which has like a specified number of orders.
Ivan Angiano. Yes.
Okay.
Exactly.
Okay.
So, but I'm just asking, like, should I think of this as sort of like a reduction of order by one phenomenon, or am I just off? A related thing that reduces the order by one is Amit Hazi's work, which might also be directly related.
Yeah, I mean, yeah, I guess
if you don't know, that's fine.
Like Frobenius, Frobenius in the quantum case moves you to a semi-simple category, and the reductive case doesn't move you at all. Cohomology is, of course, like small g cohomology is, of course, related to Frobenius, but if there's something that ought to be called reducing the order by one in the sense that you said, I guess that should be the Frobenius twist map, or the Frobenius map. So
right, and I don't know if you're actually using that or not, because anyway.
I mean, to the extent that somehow it's like tied up with the existence of this big G action on small g cohomology.
Okay. My other question was, so you wanted to somehow have something that sort of glued together multiple P cells and just some big asymptotic thing. And I can help you do some computations there. But they are distinguishable, the distinct P cells, at least in the finite type examples I know, because they have distinct eigenvalues. They have distinct categorical eigenvalues for the full twist. Which they have the same A function, but they have different R functions. So, or different C functions. I don't know what that means, but in the Grothendieck group, the homological shifts that are involved in this disappear, and you can't tell the difference. But in the actual category, they're really quite different.
Okay.
Anyway, just thought I'd mention that.
Yeah. I've done no sort of hand computations with cells of any kind. So
okay. We'll sit down and do type B at some point.
Okay.
Pramod?
Yes.
And so on the tilting module side, that there is Anderson's in the algebraic group case. There is Anderson's tensor products, which you have a tilting module. You can decompose that as a tensor product.
Yeah.
Or a smaller one with something.
Mm-hmm.
Can you see that tensor product somehow on this nilpotent orbits?
So that's I think that's basically related to the zero orbit part of this conjectural bijection. So I think that fits into this picture quite.
You have to the weight has to be far away from the zero.
Exactly. And the stuff that goes to the zero nilpotent orbit is the stuff that's very far from the walls.
And another point is that, and so far we are looking at on the character level, in correspondence with the cells. But the very interesting topic you have a corresponding to the nilpotent orbit, you have a stabilizer, you have corresponding reductive group, and you have a tilting module over there.
Yeah.
So this, I'll go backwards. So suppose that for the reductive subgroup of the stabilizer and have a tilting module, is there a way to go back to reconstruct some tilting module for the larger group, similar to the parabolic induction?
I mean, yeah, so I guess part of this conjecture is this bijection.
Yeah, that's right, exactly.
Yeah, so
whether you can make that as a category, kind of there is at least to have some kind of functorial on the category level.
I mean, yeah. I mean, even in the quantum case, I don't know of a way, like the functor goes in one direction. Like the functor can take a tilting module.
Restrict, yeah, you can restrict that to the.
And then you get like a bijection of parameter sets, but it's not an equivalence of categories, and there's not, as far as I know, a functor going the other. Oh, maybe there is actually.
Definitely, I just never thought of that question, but given this bijection, that's a very natural question. In one direction, you
no, I don't know if there's a functor going the other way. So if you wanted to make a functor going the other way, I mean, like in the quantum case already, that's a non-trivial question. So you'd have to take like the perverse coherent IC sheaf corresponding to this, and then produce the unique simple exotic sheaf on T star G mod B, and then follow that across like the ABG equivalence, and then you get like a quantum group module. But that step of going up from the nilpotent cone to the Springer resolution doesn't sound like a functor. So,
okay.
So, but do I understand correctly that this IC coherent business has been extended to the modular case?
Yeah, so IC, I mean, the definition of the IC functor makes sense. And
no, not just the definition, but the connection to cohomology of tilting objects.
No, so in fact, this, so this already it's known that this thing is usually not irreducible, but you could apply the IC functor to a tilting vector bundle, and that's also wrong. So there are counterexamples to that.
Oh, okay.
So yeah, so philosophically it should be something like, I mean, there's a very loose connection, but like, if you take it, right, so in your setting, you take a irreducible vector bundle and you produce the coherent IC, then in the positive characteristic case, you should take a tilting vector bundle and you should produce something that's whose, where the analogy is similar to the analogy between constructible ICs and parity sheaves. So somehow parity sheaves don't come from a functor, but when they exist, they're unique up to non-unique isomorphism. It's a very loose analogy, but the IC functor is not the correct thing. So